going to study multivariable functions, some of the algebra, and of course the calculus about it. Well, in the meantime, well, for this situation, we have a principal investment in our bank account at a fixed rate, so those are constant values. And n will be the number of times that investment gets reset in a way. And in this case, well, uh, if you have opened a bank account, for example, or you have made an investment, well, you're going to get interest depending on how often that goes. You know, if it's annually, semi-annually, monthly. Well, that's also going to be constant here. So really, what's going to change here, the variable is t, the time, which is how many years are we going to do this after, for 1 year, 5 years, 7 years, etc. Well, so every time we hear the word annually, that means the investment occurs how often a year? What is annual? Once a year. Okay, semi-annually means twice a year. That means n equals to 2. Quarterly, how many quarters in a year? 4. And monthly, 12. Weekly, 52. And daily, 365, right? Well, I mean, of course, we may have like 360 years and 366 days in a leap year, but well, those are special cases, so we just go with 365. All right? Well, another way to compound the interest is continuously. When it's continuously, we use a different expression, the exponential function, also known as the PERT formula, because P-E-R-T, PERT formula. We're going to compare these two expressions actually based on the results that they will output once we look at some of the examples. Well, suppose that we're going to illustrate this by using one example. So suppose that $5,000 is invested and pays 6.5% per year. Find the amount of money in the account after 10 years. After 10 years, interest is compounded. Well, we're going to do a few cases: annually, quarterly, monthly, and continuously. Well, so this number right here, which is the initial investment, that's the principal, that's P. This percent is R, which is in this case the percent, the percent rate of interest. Well, in this case, we need to be very careful because when we talk about percentages, we don't put the number with the percent symbol on an equation, on an expression. No, we need to convert this percent into its decimal form, into its decimal version. So 6.5% is the same as saying 0.065. Okay? And well, they're asking us the amount of money. Well, no, wait. Actually, the variable is n, not t. Never mind. So that's t. T equals to 10. So well, let's use the formula, the compound interest formula, to find out how much money are we going to obtain after 10 years at this rate of interest that we generate in our account. Well, so A rather, equals to P times 1 plus R over N to the NT. Okay, so the initial value, which is 5,000, and that's a 1 plus R over N. Well, R is 0.065 over N. Well, in this case, since we want to do this annually, well, that N is going to be equal to 1. And raise this to the power n times t, where n is the number of times a year, which is 1, times t, which is the number of years, which is 10. And well, so here's the thing. When working on this type of calculations, it looks like pretty straightforward to use a calculator and try to input everything. My advice: do at least some simplifications, because I've seen many silly mistakes due to error syntax or something. So at least simplify the quantity inside of the parentheses and the multiplication on the exponent. All right, so 0.065 divided by 1, well, it's still 0.065. And on top of that, at 1, that's a 5,000 times 1.006. Oh, wait, no, 0.065. And raise that to the power 1 times 10, which is simply 10. And only then go to the graphing calculator. That way it's a lot easier to input less numbers, less symbols, and having less room for silly mistakes due to syntax. Okay, so that's what I'm going to do here. I'm going to go, so that's 5,000. Open parentheses, that's 1.065, and raise that number to the 10th power. And we should get this amount over here, 9,385 with 69 cents. Wait. So, again, because in this case, so here is the thing. Sometimes when we're working on assignments, we are given additional instructions for rounding. Sometimes, most of the times, for exponential and logarithmic equations or expressions, we usually round to 4 decimal places for whatever reason. However, even though in this case we're working with exponential functions or equations or expressions, but in this case, the context behind these exponentials is about money. Well, we need to round to the nearest cent, and rounding to the nearest cent means to 2 decimal places, right? So we go to the third digit, and it happens that 7 is a number 5 or greater. That's why we round up the 68 up to 69, all right? So because in terms of money, a third decimal or a 4 decimal place is it's not meaningful, all right? So what's meaningful is 2 decimal places, which is 4 cents. So let's go back and do the following. So simplify, what was that? 93. Oh, and here is where we incorporate the units, okay? No need to write any units when working on the process, when working on the steps here, only at the very end. 9385.69. That is $9,385 with 69 cents. All right. So they're asking us to do this quarterly this time. So essentially, same numbers. I'm going to write the formula again. My advice, write it all the time. That way you can keep track of everything. About where are you inputting the certain number, on which letter, etc. And well, that's a 5,000 times 1 plus r. And again, r in decimal form, 0.065. Divided by n. Well, in this case, since this is quarterly, n is going to change. N is not going to be 1 anymore. This time it's going to be 4. And this n, it's 4 times 10. The 10 stays the same because we're still at 10 years or so. Well, so 5,000, open parentheses. I'm going to simplify this in a bit. And I'm going to multiply 4 times 10, which will be 40 to the 40th power. And, well, let's see. I can't do this on top of my head. Well, I'm going to go to the calculator. So I'm just going to do 1 plus 0.065 divided by 4. And I will get this number. So 1.01625. And when doing these middle calculations, make sure to include all decimal places, because it makes a huge difference raising with 3 decimal place number than a 5 decimal place. Trust me, it makes a huge difference, because it's an exponential this time. It's no more like a linear. Linear functions, just recall, they grow at a very low rate. However, exponential functions grow a lot faster, and well, especially when you think of when it's about money, think about your money in your money in your account. So would you prefer to do approximations or exacts, right? So it matters here. So let's see, after computing all this, So I'm going to go back to the calculator, and that's a 5,000. Whoops, one less zero. And open parentheses. What we got over here is 1.01625. Close parentheses and raise this number to the 40th power. 95, 27, 79. Well, in this case, the third digit on the decimal is 3. It's under 5, so we don't round that 79 to 80. So it's going to be up to 79 cents. Okay, let me write it down over here. So that will be 95, 27.79. All right. Well, up to this point, so it might look a little tedious to write all this big expression. Yes, I agree. And I mean, keeping doing this every single time. Well, I'm going to show you a way to generate values over here. So in this case, keep in mind that the constant values are the principal investment, which is 5,000, the rate of interest, and time, in which in this case is 10. Well, what changes in this case is how often do we look at this investment? Is it once a year? If it's twice a year, 4 times a year, etc. That's the variable in this case. Well, don't get confused about what I'm about to do, because when I do this on the graphing calculator, the dummy variable here is x, even though our variable here for the situation, for the context situation, is n. But just so this is what we're going to do. Okay, we're going to go to y equals. Let me clear. And well, that's a 5,000. Open parentheses, that's a 1 plus 0.065, which is the rate interest. And I'm going to divide this by the quantity x. Well, yes, this is the n from our formula, but the graphing calculator calls for x, okay? So it's still the same anyway. Actually, you can even program the calculator to change the variable from x to n if you wish, but I mean, it takes a while to do that programming, so I'm just going to go with x. And then raised. Well, in the newer calculators, it's pretty nice, because when you do the power, it sends everything to become the power. For older calculators, actually you would have to type something like 0.065, the exponent key, and make sure to open parentheses to make sure that everything goes to the exponent. But that's the old calculator. The newer calculators are nicer to this end. And well, that was a 10 years, and n, which is the amount, which is x. Okay. All right. I'm not going to look at the graph of this. Actually, I'm going to go to the table. And well, this is generating many different values. So number 1, for x equals to 1, isn't that the same result that we got before? That is for annually, that is once a year. And then semi-annually, twice a year. And then number 4, quarterly, 95.27 point. Well, it rounded up to 1 decimal places. That's what the calculator does anyway. But it's the same thing anyway, essentially. And well, what about, so for the next part, okay, you know what, let me change the setting for the graphing calculator, because when you have the calculator set up like this, it will just generate output values for however you set up for any input. However, if you want to know for x equals, say 5,000, do you feel like scrolling down all the way till you reach 5,000? You don't feel like it, right? It's not fun. So, well, there's a way to change that. And in this case, I'm going to go second table set. And well, we're going to configure the dependent and independent variable. So the independent variable, which is the x, instead of being generated automatically, what we're going to do is change it to ask. to ask for your favorite input. Now let me go to the table and notice how everything is gone. Everything disappeared, right? Well, I want to know x equals 1 for annually. Output. X equals to 4 for quarterly. X equals to, what was that, 12 monthly. And that's going to be our output here. However, let me see if table set, it doesn't tell me about, anyway, for the increments. I mean, that's fine. Second table, and well, I think we were asked to do monthly, precisely monthly, right? And we get 9560.9. However, according to my notes, it's 92. Okay, but for some reason, I don't know why it didn't give me one more digit here. It was supposed to give me, or maybe it's because of the dimensions of the table. Okay, continuously, well, that's where we're going to use the other formula, because continuously is no longer daily, it's no longer weekly, no, it's continuously. It's like doing it every second, or even every millisecond, or every microsecond. So your money is always working at every time. So in this case, A equals PERT, and that's a 5,000 e to the r, which is 0.065, times t, which in this case is 10 years, right? So let's go to the calculator and compute this. So let me do the calculation here. So that's in this case 5,000 e second. Okay, so to reach the exponential function, again, here we have the logarithmic function, and you want to do inverse, or the second function. So we're not the inverse, the second function. So we can reach the functions in blue, which in this case, that's where the e to the x function is at. All right, and that's 0.065 times 10. And that's the result we get. That's like the maximum amount of money that we can get out of an investment if we do it continuously. Doing it once a year doesn't generate that much. Doing it 4 times a year, it generates a little bit more, as you could see from the numerical trends in the example here. Once a year, 9,300, and then, or if we do it quarterly, that goes to $200 roughly additionally, and roughly the same. And over here, it's still around 9,500, and that's 9,500, 77.70. All right. So. Where are we going with this anyway? I mean, I know we are just, it seems like we are just working with an exponential function, generating some values, but we need to make a comparison between what's it called, between this exponential and the natural exponential. So here is what we're going to do. I'm going to go back to the table and ask the calculator to generate an investment for more trials a year. For example, 12 is for monthly. How about weekly? So I'm going to type 52. All right. What about daily? 365. That's the number it generates, right? Daily, how about hourly? Okay, so we would need to figure out how many hours are there in a year, all right? And that's going to take a big calculation, which I'm going to do by hand. I'm going to do that by hand. That is, okay, so I'm going to start with, 1 year. And I'm going to do the conversion like the stoichiometry in chemistry. So in 1 year, we have 1 year, we have 365 days. And then one day has 24 hours. All right, and with this calculation, we will find out how many hours are there in a year. Okay, cancel units, and final result, that's going to be hours. So 365 times 24, essentially. 365 times 24, big number, 87 and 60, okay? 8760 hours. So I'm going to go to the calculator and find out what's the amount of money if I do this hourly, not annually, not semi-annually, not quarterly, but hourly. We'll do that again. 8760. And well, did you see that we are essentially getting to an upper bound? You know, we're getting, well, what if I do this maybe, well, every second? Well, that's a big of a calculation. So I'm just going to input random big numbers. 1, and let me add a bunch of zeros here. Whoops. All right. So it's not, well, I forgot. There was a mistake with the 1. 1 times 10 to the 8. Well, we're still getting to 9577.7 in this case. Well, so that's because that's the maximum amount that we can obtain from compounding our interest, in this case by intervals rather than continuously than doing it continuously here. So here is where we are going to define the number E. So let's talk about that number E. It turns out that E is equal to the limit, okay, I know this symbol might be new, don't worry, the limit of 1 plus 1 over x raised to the x power as x approaches infinity. So that means if we plug in values for x, like really big, eventually we are going to reach this value, which is approximately the 2.7183 or something like that. Well, so here is what I'm going to do. I'm going to type this function. I'm going to consider the function f of x equals 1 plus 1 over x to the x power. All right? I'm going to write this. I'm going to type this on the graphing calculator. We're not going to look at the graph. I will just generate values so you can see what are we going to. So y, that's clear. So that's parentheses 1 plus 1 over x and raised to the x power. And on the other hand, I'm going to, okay, let me fix this real quick. Well, you know what, I'm just going to use y3. I'm going to use the number E, a horizontal line E, all right? Well, when I go to the table, notice how, okay, let me maybe clear. Okay, second, okay, table set. Let me do the auto. And well, notice how for large values of x, starting at 2.44, for example, they go they get increasing. Okay, let me do table set again. Hopefully those values are gone. Great. Okay, so for x equals 1, well, that's just 2. Which is not close to 2.71, kind of close, but not quite. So I'm going to increase the value of x, say 5. It's getting there. What about 10? Sort of. 100. Oh, we're getting there, 2.7 something, right? What about 10,000? 2.7181, right? So for really big numbers, that is if we were able to input the infinity number, well, which is something we cannot, right? That's because well, infinity is really not a number. Infinity is just an idea to denote something that never ends, something really big. So how about, what's that? I don't know, zillion or so. And so let's pretend this number is infinity. See how these numbers are the same? So And that checks with the definition of the exponential function. If this notation, this limit notation freaks you out, don't worry. Don't ignore it for now. That's something we will discuss later when you take calculus. Okay. In the meantime, let's go back to oh no. So we're done with this. Use exponentials in other applications. So again, there's a bunch of applications of exponential functions, such as radioactive decay, population growth, and I also mentioned those of you who are chemistry majors, you're going to look a lot of this when you cover chemical kinetics. You will use a bunch of differential equations to solve different systems, certain more complex chemical reactions, and this type of functions actually arise in those situations. And well, we have a simple model about half-life of a, and it's a very common term in general chemistry, that's nuclear chemistry. So, and they tell us about the half-life of radium-226, which is a particular isotope, and so you will have half of it after 1620 years. In a sample originally having 1 gram, the amount in grams of radium-226 present after T years is given by this equation. Notice the powers are 1/2 because we are multiplying half of the half of the half of the half. And I think that's something we discussed last time about how in some cases decreases, how in some cases increases. T is a number of years after the start of the experiment. So the question is, how much of radium will be present after 1620 years, 3240 years? So all we do is simply substitute, evaluate A at 1620. That's a 1/2, 1620 over 1620. Well, 1620 over 1620, that reduces to 1. That's 1/2 to the first power, and that's 1/2. Well, that's essentially 0.5 grams. And well, actually, we're plugging in the value of T for which we have half of the initial, the half-life, right? What about 3240, which is actually the double? If you observe these two numbers, 3240 is twice 1620. So after another half-life, we are going to have half of the half, which essentially is a quarter. And well, that's going to be consistent once we do the calculation. You'll see. Check this out. A equals 3240 equals 1/2, 3240 over 1620. And notice in this case, we don't even need calculator for this. So that's a 1/2. And since that's twice, well, that reduces to 2. And 1/2 squared, what's that? Isn't it 1/4, a quarter of it? Because half of the half is 1/4. That is 0.25 grams, because it's chemistry, and in chemistry we don't report results to our instructor or to our boss as fractions. No, that they want to see actual numbers, even with decimals. That's fine, and then at the correct significant figures and all those rules surrounding those calculations. All right, next one. Evaluate this at 48, 60. That's a 1/2 raised to the 48, 60 over 1620. And if we divide these two numbers, it looks like this is 3 times, right? 1/2 to the third power. And well, so essentially, if we rewrite this as a 1/2 times 1/2 times a 1/2 again, what do we have over here? Half of the half of the half. Well, if half is 0.5, half of the half is 1/4, which is 0.25. Now, what's 1/2 of that? That's 1/8 in the first place. However, that 0.25 times a half, half of 25, that's 12.5 essentially. Well, in decimals, 0.125 grams. And we can keep going and evaluating at your favorite value of T. But the reason to this is so we can talk about half-life. So this isotope has already gone through one half-life. What's going to happen after another half-life, and then another half-life, and then another? Remember those fractals again, like we did last time? You have one sample, half of it, and then half and half and half and half, etc. So it's going to be maybe millions of years before that 1 gram becomes nothing, essentially. Maybe not ever. All right, and that's again because we have a horizontal asymptote on the exponential function, which it will be infinitely many years before you get 0 grams of that sample. All right, and this is pretty much it for this section. There's one more thing about solving exponential equations, and this is to get started with it. So these are like the easiest case of solving exponential equations. And this is heavily linked to the fact that exponential functions are one-to-one. Remember, if f of a equals f of b, then a equals b. But in this case, we're changing the a and the b for u and v because now we're going to talk about variables to solve equations. And and again, these are the easiest type of exponential equations. Why do I call them the easiest? Because we can tell when we observe the bases of these equations, we have a base 3 and we have a base 81. For these simple cases, it will turn out that the largest number is an actual power of the smallest base. All right? And as you will see here. So number 1. Well, we have 3 to the x plus 1. Well, the number 3 as a base, it's already in its simplest form. So I'm just going to rewrite 3x to the x plus 1. However, using some number sense, we can see that the number 81 is a power of 3. All right? So what power of 3 equals 81? Anyone? 3 to the what power? So 4, right? 3 times 3 is 9, times 3 is 27, times 4, yes, that's 4. All right. Here is the thing. Essentially, this is what happens. So when we can equal the bases, we can cancel the bases to get this only the exponent equal to the other exponent, which is what happens here. Cancel the 3, and x plus 1. This reduces to a baby linear equation, and that's x equals to 3. And that's final answer here. And what else? Let's look at the other example. Well, so this could be a little tricky, even though it's still around the same idea, because, well, the lowest of the powers is 4. The highest of them is 8. However, the number 8, it's not a power of 4, right? It's not it's a multiple, but not a power. We're looking for powers because we're working on exponential equations. So in a way, it seems like it's a trap, but not really, because both numbers, 4 and 8, they're both powers of what number? 2, all right? So we can write 2 to the second power, keep the 2x plus 1, equals what power of 2 equals 8? So 2 to the third power, x plus 3. So we're not done yet. So in this case, we have the power of another power. And just to refresh this idea, whenever you have a to the m raised to the n power, this is the same as saying, what do we do? What do we do when we have the power of another power? What happens here again? Multiply a to the m n, right? So this is what we're going to do here. So let's recall this formula, this law of exponents. So we're going to multiply 2 times 2 to the 2 to the 2 times 2x plus 1, 2 to the 3 times x plus 3. And well, in this case, we got the equation in the desired form. So we have the same base, and we will be able to simplify this equation. Well, the exponentials are gone now. And again, we're going to end up with a simpler polynomial equation. Well, it's a linear equation because it seems like all powers are 1. So let's forget about the exponential. Let's focus on the linear equation. So we have parentheses. How about we use the distributive property? So that's 4x plus 2 equals to 3x plus 9. And well, you know the drill from here, variables on the left-hand side and constant terms on the right-hand side. So I'm going to subtract 3x on both sides. And that's going to lead us to 4x minus 3x. That's simply x plus 2 equals to 9. Well, we're only one step away to get x by itself. X equals to 7. And that's a really nice number. And again, like I mentioned before, these are like the easiest cases of exponential equations. Once we move on through the chapter, well, so next time we are going to start talking about logarithmic functions, which are actually the inverses of the exponential functions. Yes.
So when you turn the 4 to 2 to the power of 2,
Uh-huh.
do we have to change the sign because you put 2x plus 1 instead of minus?
Oh, you know what? Because I don't want to do the whole problem all over again, how about fix the original, turn that into a plus, right? That makes our lives easier. Thank you. So it seems like we're done with the section that we were supposed to finish next time. So, and again, I would like to use that time to go at a slower pace with logarithms or even cover more examples, more advanced examples to get you guys ready for homeworks, activities, and exams. So